Got a question?
It's on the alcohols and ethers worksheet.
Alcohols and ethers?
And, excuse me, I'm so sorry. It's actually the see the connections. And it was the... It's going from here to here. And on the notes worksheet, it says that no acid is required for that. Does that mean it can't be an acid, or it's just doesn't have to be?
That might work, but you don't need an acid. You probably wouldn't use HBr because it's expensive and caustic. Strong acids are caustic.
Could it just be Br minus?
Yeah, but you got to have a plus with it.
Okay.
What's your choice?
Okay. Got it.
What is your choice?
Potassium.
Potassium bromide. Yes. Sodium bromide. Lithium bromide. Those are common. Yeah, you don't really need the acid.
Take it back, James.
Okay, guys, let's get started. We'll pick up where we left off. First off, somebody pointed out that some of the pages in the workbook are out of order. One section was put in wrong. Okay, it goes from page 41A to, well, I don't know, 42A is over here. 67 and all of a sudden it's 41A. That section's in wrong. Please note that. Basically, after 67, you have to start going backwards. Here's 68 is over here. This needs to be flipped around. I will fix this for you if you want. We'll have to rebind it next week during lab. Okay, we don't have a lab. If you want to come by at 2:30 on Wednesday or your lab time, the first hour of your lab, I'll be available to fix that if you want. Since you don't have class on Monday, today at 1 to 3 o'clock, you can come by. Only the Monday group. Tuesday group, come by Tuesday, first hour of your lab time. Wednesday group, come by Wednesday, first hour of your lab time, if you want to get that fixed. Please, when you come by, have it open to page 41A so we can quickly do it. Okay, guys, where are we at? We need to finish up alcohols and ethers. We're looking at ethers. No class on Monday. You're starting to work on your lab for the following week, pre-lab. We will be looking at the epoxide handout today, most likely, the one that you should have printed on your own.
Today.
Okay. Did we do this one in class? Yes?
Yeah.
That one? Okay, I don't know that we're going to do any, I think we pick up here. We did the first one in the synthesis here, we pick up here. Everything else I think we've done, Rich, let me know, please.
No, you're right.
Okay, propose a Williamson ether synthesis of the following compounds. Now, when I talked about synthesis last time, I didn't use a retrosynthetic arrow. I should have. Let's introduce that. Okay, you make ethers by forming the O carbon bond. Or O carbon bond. You can make it over here or over there. Alright, if we were to form this bond, we would go back. This is a retrosynthetic arrow. Double line arrow like this. I'm going backwards. I could go back to maybe something like that plus maybe that. First off, what's wrong with this? Are these two going to react to give that?
No.
No, you got to have a leaving group, such as a bromine. Okay, I could go back to these. Can you envision these two reacting to give that? We're going backwards to the starting material. What's another possible way we could go backwards? Well, what about taking this minus and reacting it with, maybe have the leaving group on that carbon, like that. This is called retrosynthetic analysis. Going backwards, this is a retrosynthesis arrow, commonly used. Retrosynthetic analysis. Type that term in on Google, you're going to get a big old hit. Okay. Which question?
So for the one where you have like a bromine on the ends, wouldn't you need more carbon? Because otherwise it's on an sp2 carbon and can't do that.
Well, if it was one more carbon, it wouldn't react to get this. I'm not saying these are both good.
Oh.
I'm saying these are just options. When you did assess. Okay. Are they both viable, or neither viable, or is only one viable? Which one's best? Great. Where's the one on the left? We can envision these electrons doing an SN2. I'm going forward now. Okay, and I can maybe give a descriptor or something that's forward, backwards. That's pretty darn good. Can we go forward here? Why not? Okay, my double bonds are here, right? They're there, you know they're there. Does this work? No. The leaving group is not on a tetrahedral carbon. Right? So sp2 carbon. Can't do any substitution there. Now later on in this course we'll learn how, but it requires something else to be on the ring. That will never be any good. Although there is a reaction it might, but right now you certainly don't know it. That reaction will not be your best reaction. Okay, this is a better way because the leaving group is on a tetrahedral carbon. Maybe you have two different ways, and the leaving group's on a primary, and over here it's on a tertiary or secondary. Which would be better? Leaving group on primary. Okay, so you have to assess which pathway is best. That's the analysis, the retrosynthetic analysis. Here we go. These two will so these are your two star materials, but usually you want to have neutral. That is, how would you make this anion? Well, you make it from the corresponding neutral, phenol. I'm going to start going forward here. I don't have to, okay. That's it. So this would be your starting point. How do you convert it to this? Like sodium hydroxide. Then you come in with this. A lot of times, instead of showing it like this, you just keep showing arrows. And then maybe you say here, and you put maybe this on the arrow. Okay, I did it. So you go from here to here to here. With reagents, you can't put reagents on your arrows. We'll do more and more of that. So there's only really one viable way there. And that's how you synthesize a compound by WES and a little retrosynthetic analysis. Okay. If you have questions, I assume you will shout them out. Sweet Jane. Okay, did we do the first one here?
We did the first and then the second one.
And the second one. First one looks like it should have been an SN1. The second one was an SN2.
Because of the tertiary carbon.
How about the third one? Yeah. Somebody have a product here? Well, we got a strong acid. I'm going to protonate this. Okay. From the protonated nucleophile is I minus iodide. So what's the product here? Is it SN1 or SN2? Well, I'll just go ahead and show the product. The products are going to be phenol plus ethyl iodide. How do we do? I minus. And it takes here, kicks off that. This was your LG. That's what left. It left that carbon. Now iodine is bonded to that carbon. Good old SN2. Any questions about that one? Why not do chemistry over here?
sp2 carbon.
Why not ionize that off?
Yeah.
That ain't a tetrahedral carbon. Okay. First off, is that tertiary?
No.
Why is it not tertiary? Okay, don't call that tertiary. When we call things primary, secondary, tertiary, we're referring to tetrahedral carbons. sp2 carbons typically don't use those classifications. Basic. sp2, forget about it. There's only one choice here. And indeed it's SN2, because you would never make primary carbocation, it's SN2. Indeed, this is a common way to cleave aromatic ethers to create a phenol. I minus good nucleophile. That's a standard ether cleavage. Look pretty straightforward. Okay, what about cyclic ethers? You can't have a ring with the oxygen in the ring, and thus it's a cyclic ether. Well, we got acid. You're going to protonate something. Anytime you have under acidic conditions, you're usually going to protonate something, and usually the very first step. You protonate, you got Cl minus. Again, I assume you can do the mechanism for getting here. At this point, what do we want to do? They're actually going to leave two different carbons, theoretically. Which one, how are we going to do this? Do we have a tertiary site available? No, we do not. There's no tertiary site available. Who said yes?
No, I see now. I was thinking.
That's not tertiary.
Yeah, I was thinking.
That carbon is bonded to two other carbons. It's secondary. Yes, there's only one H there, but that doesn't make it tertiary.
Yeah, no, I saw.
Okay, there's no tertiary sites. What mechanism are we doing?
SN2.
SN2. So where do we attack?
Right.
We're doing SN2. We're doing an attack. We're not doing carbocation. So this is going to attack here, kick off the oxygen. What do we get? Get that right there. I mean, there's lone pairs all over the place. Does that look right? No change in stereochemistry here. We didn't do any chemistry with that carbon. No change in stereochemistry. There we go. Okay. Question. Can this react again with ACl? Show the product of that reacting with ACl again. Yes, it can. What could it do? Plus H2O. Because what do we know about, can alcohols react with HCl? Yes, refer 2 pages back. That's what we did. We reacted alcohols with HCl 2 pages back. Your product happens to be an alcohol. It can react twice. Mechanism, this becomes protonated, right? You can do what you want to do, protonated. Then what? This comes in backside, kicks that off. SN2, get that product. Question?
On the first step, we attacked on the right side because it was there, right?
It's because fine.
Well, that's part of the rule. Yeah. Yeah. Well, it may not be explicitly part of the rule. We could have attacked either. We'll say that more and more with epoxides. But yeah, since you're doing SN2, right? This is SN2. SN2 is governed largely by sterics. Yeah, it would be more favorable to attack the least sterically hindered site. So that's why we attacked over here. Okay.
Could you write that as like the chlorine on the other side and that being bad?
Yeah,
Okay.
yeah. You can show it a variety of ways. This is what? This is S. Well, as long as the high priority group is the new group, just like the O was, yeah. And this is what? R, inverted. It inverted. You can also tell an inverted how it came in. Because when this comes in, it comes in over here. The chlorine is then going to be bonded over here. I mean, here's the OH that's going to leave, here's the methyl. It's forward, but it's also sort of projected this way. Okay? Here comes the chlorine from this side. All right? I need another hand. Here we go. Here comes the chlorine. Okay? It comes in here, kicks off the oxygen. The methyl just moves back. It moves back from my view. From your view, it just goes that way, but it's still forward. Okay? So it did invert. Yes, you could show it however you want. So this can actually react twice with HCl, like two equivalents. And if you had two equivalents, you would get the product on the end.
How do you know that undergoes SN2 and not SN1?
Because it's not perfect.
Right here,
Yeah.
it actually could do SN1. Usually I tend to go with the same rule we're going with up here. I usually only going to say it's going to do SN1 if it's tertiary. Yes, SN2 could do an SN1, but I just instinctively, I'm predicting a product. We've never said any rule. Now, if I showed a product and I asked you to do a mechanism, well, then you can tell. For example, if I showed this here and I showed racemic here, then you'd know it was SN1. And then you would say, well, here's how you do SN1. Again, usually if it's primary, secondary, I usually do SN2 on secondary. If we're purely just predicting the product. Okay, how about down here? This cyclic ether with HBr. Well, we're propagating it, right? We got Br minus. Oxygen can ultimately leave carbon on over here or there. What are we going to get? Do we have a tertiary site available?
No.
Not exactly, but this is going to do this. This doesn't matter how you draw it. That's free rotation. So this left, okay. That phenyl is a benzene ring. I'm going to draw out the benzene ring. And we have a carbocation. This used to be bonded there. It left, right? Carbocation. Now that's secondary. Why are we doing this? It's more than secondary. Why is that better than just any plain old secondary? It's resonance stabilized. And resonance essentially bumps your characterization up a notch. That resonance stabilized secondary cation is just as stable as a tertiary, plain tertiary, or even better. And I say that up top, don't I? Keep in mind that a resonance stabilized secondary carbocation is just as stable as a non-resonance stabilized tertiary cation. So this is an example of considering the resonance. Now this can be hard to predict. You may actually get mixtures of both your mechanisms. But we're pointing out the fact that this cation is not just a plain old secondary cation. It's got some resonance, so it's going to be stable. And so I would predict this. Now what's our nucleophile? Now the Br minus can attack, and we'll get product. And we're going to get 1, 2, 3, 4, 1, 2, 3, 4. Then the phenyl, and we're going to have a bromine here. What's the stereochemistry going to be here? That's a chylocarbon. Going to be racemic, because when you attack a carbocation, you attack from either side. in general, usually. Make sense?
How do you know like something like that would happen? As far as like it opening up to form that?
Again, knowing absolutely that this is going to be the product, again, you may get mixtures of your mechanisms. You may get a competing we did SN1 here. You could maybe get some SN2 and end up with the bromine attacking here and that type of product.
Okay.
You know, chemistry is an experimental science. You got to go to the lab and do the reaction and investigate. You may end up with a mixture.
I feel like that is one possibility versus another.
I'm saying this is the major possibility because of the statement we made, a resonance stabilized secondary is just as good as a tertiary. So I'm seeing that as a tertiary cation. And since I see that as a tertiary cation, we're going to say that's the way we're going to go. Okay, product down here. Well, this is just THF, tetrahydrofuran. It's actually a common solvent. Okay. What if we react this with a strong nucleophile, no H plus? Strong nucleophile, your choice. Some type of. What would the product be? Product would be no reaction. Because all these reactions up here, what did we have to do to the oxygen before we didn't start it? We had to protonate it with strong acid. If you don't have any acid, it's not going to react no matter how strong the nucleophile. Okay? For example, if up here, if I had used potassium bromide instead of HBr, that would not have reacted. You got a nucleophile, but you don't have the acid that's needed to make the oxygen a good leaving group. Okay? Down here, no reaction. That's going to be different when we get to epoxide. Because of that, we can make the statement that ethers are not reactive under non-acidic conditions. They're not reactive under basic conditions. That's why THF is a good solvent when you're doing strongly basic reactions. It doesn't react under strongly basic conditions. You've got to have a proton to protonate that oxygen. Question?
Yeah.
Question?
Yeah. For the question with the HBr, do you do SN2 again? I think you erased it, but there was like another alcohol at the end.
Good point. Yeah, good point. You know, I can clarify. We just did one equivalent. Yes, very good. Sometimes instead it may say HBr excess. You'll know what excess is? Like an excess of chocolate syrup on your vanilla ice cream. It's spelled excess. Yeah. If we had used excess, you would be right there. Yeah. You could keep on going. And what else could we do here? Because we got excess reagent.
For the same question, initially, can you do SN2 or is it better just to do the carbocation?
Which one?
For the second. Yeah.
This one?
Yeah. Or is it better to get like a carbocation?
I'm missing something. Didn't we talk about that?
Yeah, we already did.
Yeah, I think we covered that. Do both. Theoretically. Yeah. I think we covered it.
Yeah.
Okay.
So theoretically, if you had
check the video. Check the video. Question. I'm sorry, yes.
oh yeah, so theoretically, if you had high enough heat, it would just go to completion, even if you had one equivalence. For that problem,
You could start getting mixtures in
Okay.
practice where some of the product reacts again. It depends on how fast this reacts versus how this reacts. If this reacts super fast, then you're probably going to end up with a lot of that compared to this. Typically, I would only go for our class and for me, I would only keep going if I like say excess. Or maybe I say two equivalents, which should tell you, hey, it's going to, I got to use it twice. Otherwise, I'm not going to say, hey, sorry, I really wanted that, and you showed this. Okay, I'm not going to. I'll try to give you some prompts to. Okay.
I remember. So like for any of those, like if you use strong acid, but with like a weak nucleophile and it's ionized, it would still react. It's like HF.
But what do you know about F minus and sulfate minus? They don't react in this class. So the answer would be no.
There would be no reaction.
Yeah. Yeah. And that's why we use those acids, because the nucleophiles don't do anything. Okay. That's ethers. Okay. But we now move on to a special type of ether called an epoxide. And I left my handout upstairs. That's why I like to put them on colored paper. Does anybody have a handout that this terrible professor can use? Sorry. This is one you're supposed to print, right? No, I was looking at it right before I left and I didn't put it on my card.
You can write your notes on that also.
Okay, guys, epoxides. I also don't have any extras because I didn't print them. That's okay. Epoxide chemistry, special type of ether. Okay, it's a cyclic ether, but it is a three-membered ring. Okay, called epoxide, also known as an oxirane. That's more of an official name, but everybody calls them epoxides. Okay, some warm-up here. This is arachidonic acid. It's a precursor to your body making things like leukotrienes, which are important in biochemical processes, inflammation, some immune responses. Arachidonic acid, your body makes it from fatty acids such as linoleic acid, things that you get from like olive oil, etc. And then your body does all this stuff with it. But along the way, arachidonic acid is converted to this, leukotriene A4. And here's an epoxide. Okay? And then from there, your body converts that by epoxide chemistry to things like leukotriene E4, reacts with cysteine, an amino acid. The sulfur acts as a nucleophile and reacts with the epoxide. Okay, that's how we get this and here. Or we can react with just aqueous acid, and we can get such a product here. You can see what's going on a little bit later, and you can digest all this transformation. But this is some epoxide chemistry in a biochemical process.
During that, like when sulfur's acting as a nucleophile, does the H that's formed like from the alcohol like off? Is that from the sulfhydryl?
Well, essentially, this loses an H and the oxygen gains an H. Is it the same exact H? I mean, okay. Synthesis of epoxides. This is nothing but a review. You synthesize epoxides in organic 1. Common way to synthesize an epoxide is from an alkene. Reacting it with a peroxy acid. The most common is MCPBA. Is what familiar? Metachloroperoxybenzoic acid. All right, we can get two different epoxides because the structure is chiral, and so you're going to get both. You get a racemic mixture in your two epoxides. Dichloromethane is just a common solvent, so is ether, so is THF. These are just common solvents. You have to just get familiar with solvents. Majority of the time when you see a solvent, it's just inert, you're going to ignore it. Okay? It's just there to dissolve things. Here's your epoxide from this guy. Well, that's not chiral. You can show it dashed or bold, either way, that it's the same thing. Okay, so that's not a chiral product, right? But if we had a methyl here, then you would have chiral products. All right? Make sense? Anything new there? So that's how we learned how to make epoxides in organic 1. I know my class did. Guys that did not have me, you did epoxide chemistry, synthesize epoxides in organic 1 from alkenes. Okay, a new way to make epoxides here. What if we took the alkene and made the bromohydrin and it's reacted with bromine and water? We would get this product. It would be racemic. That's a good old organic 1 reaction. What if we then come in here with sodium? What does sodium do to an alcohol? It creates the alkoxide. Well, then these electrons could, boom, come right in here and kick off the bromine and make your 3-membered ring. So that's more of a 2-step process. Now, you can actually use sodium hydroxide here. It's a poor equilibrium, as we talked about. It actually works here because it's so internal. Using sodium is more textbook and fits what we've talked about. Okay?
What happens to the sodium? Isn't it supposed to be like ONA?
Well, if you want to balance this, what else is formed?
NaBr.
Sodium bromide. Br minus was the leaving group. Sodium ion sits there. Okay, reactions. You can react epoxides just like we did cyclic ethers. No difference other than it's a 3-membered ring. First off, under acidic conditions, just like we started today on the other handout, using HX. We have a rule that we're going to also go by. We only do SN1 if we see a tertiary site. Otherwise, you do SN2. Okay? Because we're still under ethers. Okay? The one thing new we'll have here is that SN1 with epoxides gives inversion. SN1 gives inversion. That is only for epoxides. It's because of the small size of the ring. Okay, but that's new. It also sounds odd, doesn't it? Why? We'll explain.
Do you have the same rule where if you have a secondary that is resonance stabilized with that, would you still treat that as a tertiary?
Sure, sure. I mean, that applies to any carbocation chemistry. Yeah.
Will SN2 still give inversion, or is just?
Yes, SN2 will still give inversion. Yep. Okay, so let's do this. We're under HBr, we're going to protonate. Okay, you can protonate the oxygen just like any other oxygen. I'll skip that mechanistic step. We've got Br minus. All right, do we have a tertiary site available? The oxygen can leave this carbon or that one. Either one of those tertiary? No. So what mechanism are we doing? SN2. So we don't have to worry about that yet because we ain't doing SN1. So which carbon are we going to attack? Left or right? the least sterically hindered. Kick the oxygen off of that, and what do we get? We get this here. The bromine is now bonded to the carbon. That carbon is not chiral, so it doesn't matter how you draw that bond. Free rotation, I could have drawn it, it doesn't matter. Okay? Oxygen leaves. Oxygen is forward, and it's connected over here. It leaves, but it's still forward. Okay? There's no change here. There's no chemistry there. So it's still forward. It's just no longer bonded over here. Got ticked off. So no change. And there's your product. And really, there's nothing new there than we were doing on the other handout. Is there? Nothing new there. Have I seen anything new there? No. Let's do the one down here. Okay, we're going to protonate. We're under acidic conditions. We're going to protonate something. We got Cl minus. Okay. Do we have a tertiary site available? Oxygen can leave top or bottom. Tertiary site. So what mechanism we're going to do? SN1. So what do we need to do? This is going to ionize off. What does that give? Now here's where we're going to have to talk about how we get the inversion. But let's just go ahead and ionize it off. So it left. It's still forward though. There's a methyl here. And this is a cation. Okay, this used to be bonded here, but it left, and now that's a cation. Now, traditionally, and up till now, then we attack here, and what's the outcome of this carbon? Racemic, because you attack either side. Well, you don't get racemic, you get inversion. How do you get inversion?
Back bonding.
Well, backside attack is inversion, but why would it only do backside attack at a cation?
It's still back bonding because it's not completely leaving yet, right? Because it's epoxide.
The reason is the leaving group, okay, is still close by, and it's still only 2 or 3 bonds away. It's still close by. Let me ask you this: do you think those electrons will be attracted to that plus charge?
Yeah.
Sure, that's physics. Why would that leaving group leave well, it can't just go way away because it's still bonded close by. And if it's sitting there, is there going to be any attraction? Yeah, physics. There's attraction here. And I've called that back bonding before. Now, if you make it so much attraction that it's a bond, well, then it's a bond. It's actually somewhere in between. That oxygen's forward, okay? There's the original epoxide, it's forward. It used to be bonded, okay? Pretend it's bonded. Okay, it broke away, but it doesn't go way away. It's still kind of attracted. So it's still sort of blocking the approach of the nucleophile. Okay? If it had went way away, then the nucleophile can come in either side. Either side. But what if I'm sort of here, and I'll turn because the molecule's doing all types of stuff. I'm kind of attracted. Which way you want to come in? You see, I kind of blocked it. It has to come in that way because there's some attraction, some back bonding. Okay? And it's hard to show this because I could show it right here. But if I attack here, kick that off, that's SN2. So I can't just do that. But I also can't just show a free cation because we know if we attack that, I should get racemic. It's somewhere in between, and we know if you do this in lab, you get predominantly inversion, even though, also, if it was SN2, we wouldn't be attacking down here. We'd be attacking up there. So what is it? It's kind of a blend. It's a blend of SN2. It's a blend of SN1. That's why we're down here. But it gives inversion, which seems like it's SN2. Hard to show mechanism. You pretty much just have to show the outcome. And the outcome is the OH is up here. It just left, but it's still interacted. It caused the chlorine to come in opposite. It caused the chlorine to come in this way, and it pushed the methyl that way. The chlorine came in opposite because the OH was interfering with one side, doing some back bonding, some interaction. And ultimately, you end up with inversion, which seems like SN2, but we didn't do SN2. Again, if you had done SN2, you would have attacked up here, and you would have shown a concerted mechanism. They say blended mechanism. It's hard to show precisely. In terms of an outcome, there's your outcome. Okay. The very first reaction you do with alkenes is typically a reaction of an alkene like bromine. Br2, bromonium, and then from the bromonium you do what? Backside attack. Okay. Backside attack sounds like SN2. What if you had this bromonium? Which carbon does the Br minus supposed to attack? One over here. Remember from organic 1, right? Now my guys, when we covered this, we had not even covered SN2. All right? We said, okay, if you're going to make cation, would you make cation on left or right? You'd make cation here, and I said, well, that's where it's going to attack. But guess what? And then we attack like this. But this is actually totally opposite of good SN2. This looks like SN2, but if it's SN2, why did we attack over there? It's because actually the attack of a bromonium is just like this. It's just when we covered bromonium, we were not ready to discuss these things as much. Because this bromine doesn't like to be bonded. It breaks away. And if it broke away, you'd get that. But it's so much interaction here that's why you get inversion. Okay? It's analogous to the bromonium chemistry. If you think about it and go back and review your bromonium chemistry, okay, so I had that already drawn. You know, you attack here, kick off the bromine, but think about the discrepancies there. Okay, we used H plus and halide nucleophile. What about using H plus and some other nucleophile? For example, this is what? This is H plus, and what's the nucleophile here? Water. As we said, sulfate ain't a nucleophile in this class. Water, it's aqueous acid. Water is going to be your nucleophile. Okay? Sulfate, no. So, you protonate, we can do that. Water is your nucleophile. Do you see a tertiary site available? No. So what mechanism are we doing? Good old-fashioned SN2, and that is nothing different than what we've done there. We attack at least sterically hindered site, kick that off, and we get OH there, and we get the water bonded to the carbon. Okay? We just made that bond. please don't just magically lose an H. When oxygen makes a bond, you have this. We have to lose an H to go neutral. Now the conjugate base, I'm not going to show the electrons out. This will take the H, leave the electrons behind, and we get our final product. Which is that there, plus what? What did we reform? Yes. This is really sulfuric acid, your catalyst. And ultimately, we're adding water to this formula. It now has water added to the formula. We've added water with an acid catalyst. How does that look?
So that's like all you're given as far as like the reaction you use the water as a nucleophile.
What other nucleophile would you use? Okay. How about down here? Here we have sulfuric acid methanol. Now this is usually aqueous, but anytime you have something else, you're probably going to use something else. If you don't want an aqueous acid, you could use like HF here. That would be a dry acid. And the F- won't attack. Here you're going to protonate using your acid catalyst. And then methanol is going to attack. Which carbon, top or bottom? They're the same. If you have a symmetrical epoxide, they're the same. Attack either one, it gives you the same product. I'll attack the top, kick it off. The oxygen, OH just got kicked off. We are doing SN2, right? I didn't say that. Are either one of these sites tertiary? No, secondary. We're doing SN2. And so what do we have up here? The oxygen came in backside. So we made that bond. And then the acid, okay, just like above. I'm just going to show that O-methyl. Just sort of condensed a little bit. Right? Sulfuric acid, the sulfate takes the H, leaves the electrons behind. Now you have two lone pairs. There you go. This product is chiral. What else we're going to get formed here? We reformed sulfuric acid, yeah. What else is formed here? No. There's no enantiomer formed here. You start with this epoxide. Hold on. Hold on. Hold on. I forgot to go. Tell me why there's an enantiomer. Good. Good. Yeah. It doesn't automatically have to be an enantiomer. But after I looked over here, is this optically active? See, this is not, even though there's projections here, that doesn't mean it's chiral. This is not chiral. That means it's not optically active. If this is not optically active, your product can't be optically active. So that's how I figured, I'm like, hold on there. And if this is all you got, that'd be optically active. It's going to be an enantiomer. How do you get the enantiomer? Actually, if you attack down here, you would get the enantiomer. Because it would look like what? If you attack below, you'd have the O-methyl at the bottom, but it would be back. And the OH would be here. Are those enantiomers? Yes, because if you take this and flip it over, then the OH will be down, but it will be back. Okay? Yeah, see, an enantiomer comes from attacking the other site. If you work through that, you'll see that that's how you get the enantiomer. And you really have a 50-50 chance of attacking either site. Okay, how about this one here?
No reaction.
Product of this reaction. That's a good nucleophile. That's your acetylide anion. But it's an acid to protonate.
It's just going to react with each other, right? Yeah.
I didn't hear you.
Huh?
I didn't hear
I'm
you.
talking to myself. I thought like they would react together, right?
This
Because
would be no
it's a strong
reaction,
base.
right?
Yeah.
Why is that no reaction?
Carbene is a
This
strong
is H plus source, right? These electrons are going to react. That's very strongly based. This is going to react. You can't say, hey, only protonate that. Well, that's not even an anion. Where's my chart? Right there. That's a negative charge. Okay. These are not compatible. You can't have your cake and eat it too. Okay, you can't have acid and a very strong nucleophile. Up here, the nucleophiles were acid compatible, neutral, or Br minus, which is acid compatible. Okay? Under basic conditions. But I thought ethers were not reactive under basic conditions. Yeah, but epoxides are, because of ring strain. Please look ahead. Please make sure you bring your hand out next time too.
You.